Hello, everyone. This is Mr. Smith. Welcome back. Thanks for joining me talking chemistry, specifically bonding, more specifically ionic versus covalent bonding in terms of their composition, in terms of how they are formed, and in terms of the properties that we see when we have and occur comparing molecular compounds, molecular covalent compounds and ionic compounds. So this is one of kind of the go-to slides we have. Molecular covalent comprises of nonmetals. They share their valence electrons to add up to the octet rule. We've talked about naming earlier in the year. We can see these Greek prefixes. And what does sharing look like is what this picture is trying to show here, where the valence electrons of oxygen and hydrogen, the way their orbits and orbitals are kind of merged together quite a bit. And we'll talk about that more throughout the unit. But in this context, we just really care about the vocab of sharing valence electrons. As opposed to ionics, there's no sharing, it's a transfer of electrons from a metal, which is going to become a cation, to a nonmetal, which will become an anion. And so these are comprised of metals and nonmetals, and again, they are transferring. And in terms of naming, we're not going to see the Greek prefixes. We really wanted to, back in the day when we first had kind of two classes of compounds based off of two sets of physical properties, we wanted one set of properties to have this naming system and one set of properties to have this naming system. I wasn't around back then, but that's my story and sticking to it, that the two different types of compounds needed to have two different names because their physical properties were so different. Years later, centuries later, we figure out about the electrons sharing versus transferring, but still the physical properties were different enough to kind of demand a new naming system. So what kind of properties are different? So let me pull this over. Actually, let me pause for that. One step ahead of myself. Second slide here. And so here are kind of there are many of the differences between ionic and covalent compounds. First, the individual unit for an ionic compound we call a formula unit. All those positive cations and anions isn't just this discrete one-on-one sodium and chloride. It's actually a whole bunch of sodiums with a whole bunch of chlorides that go on and on and on, as opposed to an individual molecule of, say, carbon monoxide, one carbon, one oxygen bound together, that can exist by itself, as opposed to one sodium, one chloride that will not be existing by itself. It's going to be surrounded by many other sodium cations and many other chloride ions. And so we use the vocab formula units. Bond formation, again, transfer of valence electrons for ionic, sharing of valence electrons for covalent. Types of metals, again, metal and nonmetal for ionic, nonmetal for the covalent. Now, physical states. So ionic compounds at room temperature are just about exclusively solids. Rare exceptions of liquids. In fact, you can do graduate school level research tracking down talking about ionic liquids at room temperature. So overwhelmingly, you're getting yourself solids. As opposed to covalents, there's a little bit of everything. There are some solids like sugar. There are some liquids like gasoline and ethanol and methanol and some, I hope I said liquids, liquids like gasoline, there we go. And then gases, things like the air we breathe is entirely covalent. Things like propane and acetylene and methane, those are gases, covalent gases. And so covalents are actually pretty widespread out in terms of physical states here presently at room temperature. Now that's partly because, I guess entirely because, by definition of the melting points, ionic solids have typically very high melting points, well above 300 Celsius. You know, what is high? Is it 100, 200, 300, 500? The point is, it's higher than covalents. Most of your covalents are very low melting points. If you think of a solid like wax, that melts very quickly. Doesn't take a lot of heat. If you think of and wax is a covalent compound, it's called a hydrocarbon with a whole bunch of hydrogens and carbons there. As opposed to your ionic solids, things like salt, you really can't even picture it melting. It takes quite a bit of heat to make that happen. Things like sugar, which is covalent, melts fairly easily. And so a general rule with minimal overlap really is that ionics have very high, relatively high melting points, and covalents relatively low melting points. Some a little bit above room temperature, some way below room temperature, and that's what makes it a liquid or a gas at room temperature. And so if it has a low melting point, like say a water, the melting point is the melting point of 32 degrees Fahrenheit. Anything above 32 degrees Fahrenheit is going to be a liquid, and so relatively a low melting point compared to something like sodium chloride, which takes hundreds of degrees Fahrenheit, not 32, but maybe 500, 600. I'd have to Google the answer to see the melting point of sodium chloride, but definitely relatively high. Solubility in water is not really a big difference between the two. There's actually quite the range of both ionic and covalent compounds. Typically speaking, your ionic compounds could be more soluble than some of your even soluble covalent compounds. So this isn't as big of a differentiation that some kind of PowerPoint slides and textbooks presume. There are some ionic compounds that are not soluble at all. There's some ionic compounds that dissolve quite well. We get to talk about this in a later unit called our solution unit. The conductivity, though, is a difference, and conductivity is something that can actually demonstrate the electrical conductivity in an aqueous solution. That means dissolved in water. So a solid doesn't conduct unless it's a metal. So both of these ionic compounds, covalent compounds, do not conduct as solids. But when dissolved in water, ionic compounds are very good conductors. In fact, we use the term electrolytes. Covalent compounds, not so much. And so I can kind of show that off a little bit briefly using a PhET simulation here. And so here's a sugar. Here's our conductivity. So to have something conduct, it's like my computer's lagging a little bit. To have something conduct, you need, I guess, both ends of the battery to connect to that light bulb. So one of those is connected by a wire directly. The other one has to go through the wire, through what we call the electrodes, but this water has to conduct. Water by itself actually doesn't conduct very much at all. It's the other stuff you put in there. That other stuff not being sugar. So sugar is a covalent compound using the elements carbon and oxygen and hydrogen, all nonmetals. And so notice this light bulb is not turning on. But if I switch to salt, in fact, I'll reset it. And my computer lag a little bit, it's catching up to us. So here's salt. Now salt is sodium chloride, NaCl. Now we get little beams of light. So it's kind of a cute little simulation. So thank you to PhET. And the more salts I add, the bigger those beams of light get. We'll talk about that again in a later solution unit. We'll call this a colligative property. But for now, the ionic salt conducts electricity, and the covalent sugar does not. So if I were to add more sugar, these beams of lights aren't going to get any bigger. As I keep adding and keep shaking, these beams of light are not getting any bigger. Sugar does not conduct when it is dissolved in water. But if I were to add more salt, there's the salt, here's the add, and hopefully you see those beams of light get a little bit bigger. All right. So thank you for that. So I wanted to kind of reword all of that and bring this over. It's pretty good. Let me make it a little bit bigger for you. Get myself out of the way. And then let's start typing. And so from the element type, so covalents come from the nonmetals. And again, the nonmetals, if I bring another periodic table over, I'll put myself right there in the middle. And here's all your nonmetals. So all of this kind of corner over here would be your nonmetals, and then your metals would be most of everything else. These and these and these. first two columns. You can pick up some vocab, post-transition metals, P-block metals, the lanthanides, the actinides, the transition metals, the alkaline earth metals. One thing to know that I almost got wrong here, hydrogen is considered a non-metal, as are all the noble gases. You do have this gray area of a metalloid. Typically the metalloid does more more non-metal things. Aluminum's a metal, that's what caught me. So aluminum does metal things. The rest of them, being a metalloid, they have kind of a blend of both properties. And so let me pull those through. So these metalloids actually typically, and carbon doesn't count, so I'm going to erase that. So boron, silicon, germanium, arsenic, antimony, tellurium. Those are your metalloids. You can kind of Google things like polonium and decide if it's a metalloid or a metal or not. Polonium is so radioactive, which we'll talk about in a couple of units. It's so radioactive that it doesn't really matter if it's a metalloid or not. Acetine is so rare, same thing, doesn't really matter how it's kind of classified, because there's not really enough on Earth to really be concerned with. But boron, silicon, germanium, arsenic, antimony, and tellurium, there's plenty of that on Earth, and we do kind of care about those. So typically your semi-metals, your metalloids, have more of a non-metal feel to them. But again, looking at the periodic table, when you see kind of a slide like this, and it says, metals and nonmetals, how do you know which elements are metals and nonmetals? That's what the periodic table can do for you. So I'm going to click this. I'm going to type in for the covalents, the all nonmetals. I'm going to highlight that and make it red. And then over here, the ionic compounds to be metals and nonmetals, and that's a much better font there. So the covalents are composed of molecules. Red, pretty sure I misspelled it, but I can fix it quick. And then the ionic compounds are, hopefully not surprising, composed of ions. Red some more. All right. So move myself over here, change my font from 8 to 14, and let's see what we can do. So formed by what? So go ahead and take a moment. Formed by covalent molecular compounds, so formed by sharing electrons, specifically valence electrons, while ionic compounds are formed by a transfer. In fact, I'll use my own words, gaining and losing, again, those valence electrons. Types of bonds, and so these molecular compounds, covalent compounds, have covalent bonds. So let me up those sizes. Thanks for your patience. Then over here, what type of bonds hold together ionic compounds? Ionic bonds. So not too surprising there. Okay, so over here, melting point. So this is kind of the new property. Covalents typically have low melting points. Make that red, make that larger, and we are good. Over here, your ionics have generally, typically high melting points. Click the wrong button, but I can fix that real quick. All right. Physical states at room temperature. So we have some extra vocab words. Brittle, crystalline, solid. So brittle means it falls apart easily. That is true for your ionic compounds. So let's make that red. Let's make it bigger so you can read it. And then the covalents would be either a gas, a liquid, or a solid. There we go. Make that a bit bigger. Make it red. And last but not least, conductivity. Conducts electricity, specifically when dissolved in water. Now, again, as a solid, neither is going to conduct electricity. But when dissolved in water, covalent compounds not. So red and 14. And then over here, ionics, when melted, we actually pick up the vocab molten, which is a nice vocab word. Melted, or specifically when it is dissolved in water, which picks up the vocab aqueous. And so those are the differences. Just because of how those electrons are shared versus transferred, those charges you get, that the ionic compound gets to form with those charges, changes the physical properties. And what is the difference between something like salt and water is how those valence electrons are treated in the context of these bonds here. So thank you so much for your time. Good luck on the worksheets, and remember, please remember, chemistry is everywhere.